terms. So, today we're going to be looking at thin film interference. So, what happens when we have light interacting with some kind of really thin surface, because it's going to refract into it and then reflect while it's refracting, and go through all of this stuff. Where this comes into play, there are two main areas where you've probably seen this in real life. One is with the soap bubble. So if you've noticed, if the light hits a soap bubble just right, you see kind of a rainbow, just like you see here on the slide, where it's that kind of rainbow-looking effect. You can also see the same sort of thing if you ever see oil on asphalt. So if you ever notice that in a parking lot that the asphalt or blacktop, whatever, if you notice it's got that kind of rainbow type effect going on, it's because there's a very thin coating of probably motor oil on that surface that's allowing the light whenever it hits there to do all kinds of reflection, refraction, and interference with itself in order to get those colors to appear essentially like a rainbow. These things do only work though if it's a very thin film. So that's why if you just have a container of soap solution sitting on the counter, you're not going to get that rainbow. Or if you just have a big puddle of motor oil, so like a fresh spill, there's also not going to be a rainbow there. It's just going to be black because it's got to be a very thin medium for this stuff to happen. Okay, so basically what happens, excuse me, in one of these is we have our light coming in, and so this is going to be basically a soap bubble. And again, if you think about how thick the actual walls of a bubble are, it's incredibly thin. So this is either a very magnified image, or it's just, inflated for demonstration purposes. But anyway, so we have our initial light source S that's coming in, and it's going to refract when it goes into the soap bubble. And remember, anytime there's refraction occurring, there's also going to be reflection. So there's going to be one ray of light coming out here. Then it refracts down through, and then refracts out the other side to go inside the soap bubble or come out of the soap bubble, depending on which side we were starting on. And again, that's going to reflect there, and then also refract as it goes back through. And technically, it's going to keep doing that over and over again until it just loses its strength. But it's really only this first one that we really care about. There are others that we could do, but I've never seen AP Physics worry about any of the other ones further down the line. So no need to worry about them. So what winds up happening then is essentially that process that we just went over. However, one of the big things that happens here is the inversion of some of these light sources. So anytime that we have light reflecting off of a surface with a higher index of refraction than the one it was in, so you can kind of think of it as like hitting a harder surface in a way. Like it doesn't matter the actual hardnesses of the surfaces, but you can kind of picture the indices of refraction in that sort of mindset. So whenever that light from the air comes and it hits the bubble, since the bubble has a higher index of refraction, this light wave is going to invert. So essentially, if I had it going like this, so at this point the light wave was moving on its downward path. It was heading toward the trough. So we would expect it over here, if it were to just reflect, to make that kind of trough thing. But since it's inverting, it's actually going to hop up on its own. Then that light's going to continue on, just like it would. And then it hits here. Now, since this is a quote-unquote softer surface where the index of refraction is lower, it's not going to invert. So because it was kind of on its upward trajectory, on its way back, it's going to continue its upward trajectory and go on and do its thing. And of course, I have that drawn, really poorly with the wavelengths. But the important thing is what happens at these boundaries. So here it's going to invert. So if it was going down, it's going to flip its direction. Here it's going to stay the same. So if it was going down, it's going to continue going down when it gets there. And so where that becomes important is when we start doing the math with these. So we have two equations, one for constructive and one for destructive. Um, and it's basically the same. It's basically the same equation. It's just whether or how we take into account that inversion of the light. So for a constructive interference, the wavelength of whatever color it is going to be equal to 2 in t. So 2 is just, obviously constant. N is going to be essentially which, as this thing is bouncing all over the place, which bounce is it? Again, I have never seen AP Physics use anything other than this very first bounce. So your N is basically always going to be 1. But just in case for some weird reason they decide to throw something else at you at some point, just know that that can be something bigger than 1. T is the thickness of the material, so whatever this happens to be. And then M, N is not, I was going crazy. M is the integer, how many bounces it is. My bad. N is going to be the ratio of the indices of refraction in the material. So, in most cases, it's just simply going to be whatever the index of refraction is for this material here, because it's a ratio of this divided by the one on the outside. And since we're usually going to be using air, it's usually, in this case, it'd be 1.33 over 1, which just comes out to, of course, the index of refraction of the bubble itself. But we could have something where, like, maybe there's some glass underwater or something like that, where you'd have to do, 1.5 over 1.33 or something like that. So just something to be aware of, that this N here is not just the index of refraction of the material, it's a ratio of the indices of refraction. And this all comes from the math that comes into getting all this stuff together. There's some real gross derivations that you can look up or try if you really want to, but there's no reason to. And then for constructive interference, our integer here has a plus 1/2, because since these have, since this light ray has inverted, it's going to be off by a half of our original light ray. So we need that 1/2 there so that we can basically shift them back into line to get that constructive interference. Because we want these two, by the time they leave and they start heading on that parallel path with each other, we want them to be constructively interfering. So basically what this equation does between the thickness and the integer and all this other stuff, and there's a bunch of math and things that cancel out, but it winds up essentially taking this path here and comparing it to this difference of path there, and basically boiling it down to how many, like the difference in wavelength between them. So just like with diffraction, where it didn't really matter how far apart the two things were, it was more so how many wavelengths off of a distance did the light have to travel to get from, the slits to the wall. It's the same thing here. We're looking at the difference in wavelengths. And so we want the wavelengths in constructive to be off by 1/2, because when this inverted, it was already up by 1/2 to begin with. So that's why we're using this plus 1/2, because we want those wavelengths to be shifted off by 1/2, because that's actually going to shift them right back into phase with each other. For destructive interference, it's the same thing. So wavelength 2, N is the index of refraction ratio, T is the thickness, and then M is going to be the integer. Again, basically 1 99% of the time. I've never seen M be 2. I don't think I ever saw it in college either. It might have more applications when you get into calculus and stuff like that. But anyway, so here we have the whole M, because since these have already been shifted by 1/2, we want them to be completely out of phase with each other. So as long as they just line up with what they were doing to begin with, they're going to destructively interfere. And so basically what happens between the fact that different wavelengths of light are going to refract differently when they go into the material, because they have different speeds of light in it, that's how you wind up seeing that certain rainbow, because at certain angles those wavelengths are going to be traveling different distances. And so based on that very minute difference in angle between those parts in the oil slick or the bubble or whatever it happens to be, between that light source and your eyeball, there's going to be one color that really predominates over the others, because it's going to be the strongest in terms of constructively interfering. And so that's why you see it. And again, it's just like a rainbow where each individual part of the bubble, you're going to be seeing a different kind of color, just like with the rainbow. Each individual droplet of water is going to be throwing off its own unique wavelength that just happens to be at the right angle to hit you in the eyeball. So for lens coatings then, so this is, again, another example of a thin film. The difference here, though, is that we're going from one surface into another and then into a different surface on the other side. So instead of it being a bubble where we had the same medium on either side of the thing, now we've got different stuff here. Same sort of thing is going to happen though. So light is going to enter our first medium. In this case, it looks like it's water, and this is probably glass. So maybe a wet window or something like that. So when it refracts here, our light is going to invert because it hits a harder material. And again, hard. Higher index of refraction. So we wind up with an inverted wave coming off here. Then this light enters through, refracts, and is going to refract into our new material as well, which means then that it also reflects. But whenever we look at these indices of refraction, I can tell that N2 is a higher index of refraction than N1, so it's also going to invert whenever it reflects off of there as well. So just slightly different. So because now we have two reflections happening, since they both flipped and they both flipped the same amount, they should hopefully be, completely in phase with one another. So whenever we go to look at the equations for this one, they're actually going to be flipped between the constructive and destructive. So because those things are completely in phase with one another, since they've both inverted, we are going to be able to use just simply m being 1 and then just having the 1 down here. We don't want that 1/2 because they already should be in sync with each other. We don't have to adjust for the fact that one of them flipped, because since both of them flipped, they're basically doing the same thing. They're just both upside down if you want to look at it that way. With destructive interference then, we're going to have that 1/2 because we need to shift them 1/2 wavelength completely out of phase in order to get that to happen. So it's the same equation for all of them. It's just a matter of where do you put the 1/2, and it's just simply where do you want that phase to be. First off, do you want them to be constructively or destructively interfering? And then you need to look at, are they already trying to kind of line up, or has one of them flipped? In which case you need to look at that. So not too terribly difficult, just something to keep in mind. Also, I don't think that these equations are on your equation sheet. I could be wrong. I don't have an equation sheet with me at home. So you may want to double check, but it is a pretty simple equation to remember. It's just 2nt over m is equal to wavelength. So where this application comes into play are interference and lens coatings. So as you can probably tell on the recording here, my glasses actually don't have this thin film anymore because I painted a few years ago with them on, cleaned the rollers off with a hose, and it spun paint, and the only way I could get it off was a ultrasonic cleaning, which took the coating off of them, unfortunately. So that's why you can basically see the notes and the recording software I have on the other monitor in my glasses, because they don't have that lens coating anymore. Now it doesn't make any difference for me. It's just pictures and stuff are annoying. But basically, that lens coating is designed to be made of a certain material that has a certain index of refraction, and it has a certain thickness, so that when visible light hits it, there's going to be as much destructive interference as possible. So you're always going to see the reflection of something happening, just because there's no way to hide it. But with the anti-glare coating, which the glasses on the bottom have, we can get a lot of destructive interference happening, so that we can eliminate a lot of that glare, or a lot of that stuff. And then one quick reminder, just as a heads up, because we're talking about the two different materials here. So this N value is going to work the exact same way that it would with if we just had a normal thin film like this guy, because even though we have this 1.5 down here, the light that we're concerned about never actually enters this medium. We only care about the light that was in our initial medium, then in our first thing here. The only thing this does is determines whether or not this light inverts when it reflects. So because of that, we don't have to worry about putting the 1.5 in there anywhere. So whether it's a thin coating or a thin, just normal film, it's always just the ratio of the indices of refraction of the medium that the light is doing most of the reflection and refraction with, and then the medium that it began with. Alright, colors on an oil slick are caused by reflection, refraction, and give you a couple seconds to think. Pause if you need to. So it's going to be both those two things, and then it all depends on what happens with those wavelengths after they leave the material and they line back up. So just like with diffraction, what's happening with the wavelengths, interference is going to be the answer here. So it's not going to be diffraction because those waves aren't, like changing their direction when they pass a boundary. That's what caused our interference with light when it passes through a double or a single slit, or a diffraction grating. But interference here is going to be the answer. And polarization, we haven't looked at yet, so hopefully didn't pick that one. Alright, light with a wavelength of 550 nanometers shines on a soap bubble where the index of refraction is 1.33. So I want to know what the minimum thickness of the soap bubble is to minimize the intensity of the reflected light. So I'm going to give you a minute or so to do this. Go ahead and pause, because I'm just going to go right into it. So hit pause, work it out, and hit play. Alright, so because I'm looking to minimize the intensity of the reflected light, the lambda that I want, I'm going to want the destructive equation here, because I want this to be completely minimized. So since this is a soap bubble, if I have my N1 here, which is going to be the 1.33, my N naught is going to be air, which is 1, and again, because it's a bubble and it's not a coating, I know we also have N naught on the outside. So whenever this light enters, it's going to invert at the first boundary, but then it's just going to simply do its normal reflection, go back the same direction on the second one. So for this case, I want to use the 2nt simply over m. Because there's only one of those light waves is inverting, and I'm looking for destructive, I know that when that light wave inverted, it already shifted it 1/2 of the way out of phase. And so I need to make sure that it stays out of phase to have that destructive interference. So I do not want the 1/2 down here. And then a neat thing that we can look at if we look at all of the units in here. So wavelength has units, usually in meters. And since n is just the index of refraction doesn't have units. T is thickness, that's also going to be in meters. And then m, since that's just an integer, and that integer is basically 1 all the time, there's no units there. So the only units you have are these two distance ones. So if you want to go to meters, you can, but by no means is it required. And since we're talking about really, really small thicknesses, with this 550 nanometers, it's totally realistic to leave it in nanometers. Of course, you could put any units in any metric system that you wanted to do, but like in terms of actual real-life application, it would actually be useful to leave this alone in nanometers to keep it away from meters. So anyway, so the wavelength we know is going to be 550 nanometers, and that's equal to 2. And then n is the ratio of the indices of refraction, so 1.33 over 1. Again, you could simplify that down to just 1.33, but just being careful to make sure you don't always ignore our outer index of refraction value. Times the thickness, and then over 1. And so when you go to solve that, you should get 207 nanometers. So, any questions you got, let me know.